Hey, what's going on, guys? Let's see how we can do this problem right here. The question is asking you to find the work, heat, and these change in internal energy, right? So let's see how we can do this. First of all, let's see how we can calculate the total work. So if you look at this one, this is a triangle shape. So to find the work of this one, we can use area of the triangle, right? If you find the area of this triangle, that's going to be the work, total work. But if you want to find individually, for example, if you want to find the work of this one, you have to take the area below that line right here. And for this one, area below that line. So same thing goes to everything. And for a vertical line, the work is going to be 0 because there's no area for area under vertical line, right? So that's how we do this. But when we have triangle circle, the area inside the triangle is going to be the work, total work. So here the total work is going to be area of the triangle. So let's see how we can calculate this one. W is going to be area of the triangle. Area, that's equal to half times base times height. Right. So here half, the base of this triangle is volume difference. 60 minus 20, that's going to be 40. So 40 is the base. And then this is the height is 1 atm, right? Because 2 minus 1, that's going to be 1. So this is going to be 1 atm. Since this is in liter, this is in atm, we have to convert this one into joule. To do that, we have to simply multiply this one by 101.3 joule per atm liter. So this is the value we multiply whenever we have liter and atm. So that's how we do this, right? So if you calculate this one, that's going to give you 2026 joules. This is our work. So what about delta U? Whenever we have a cyclic process, whenever you have one thing is beginning and ending in same thing, like it doesn't matter triangle or whatever the shape it is. If it's a cyclic process, the delta U is always 0. So here delta U is 0. And what about the heat? To find the heat, what we can do, we can use the first law of thermodynamics. That's delta U is equal to Q minus W. If the delta U is equal to 0, we can say Q is equal to W. Because if you plug 0 and move the W to the other side, that's going to be plus W, right? Therefore, heat also going to be same as work, 2026. So let's see how we can find this for each process. So let's look at 1 to 2. Let's say this is 1. Let's choose a different color. So this is 1, 2, 3. So let's see how we can find this one for each process. W1 to 2, right? 1 to 2, what's going to be the value? If you look at this one, this is an isochoric process or isovolumetric process. You can call it in both ways. So isochoric process means the volume is constant. So whenever we have isochoric process, the work is always 0. As I said before, like if you look at this diagram alone, in PV diagram, this is a straight vertical line. There's no area under this line, so therefore this is 0. Or you can analyze in different way. W is equal to P delta V. Delta V is going to be 0 because final and initial volume is going to be same. If you subtract them, that's going to give you 0. So that's going to make everything 0. So here the work is 0. How about the heat? If the work is 0, we know that in according to first law of thermodynamics, delta U is equal to Q minus W. If the work is 0, delta U is going to be equal as Q. So whenever we have an isochoric process, if the volume is constant, we can use this equation. Q is equal to NCV delta T, right? And if you want to find the U first, you can use this one. Delta U is equal to NCV delta T. But Q changes according to the situation. If it's an isobaric process, for example, if it's a constant pressure, constant pressure, we have to use NCP delta T to find the Q in that case. But for delta U, it's always NCV delta T. It doesn't matter isochoric, isobaric, or anything. It's always going to be NCV delta T, right? So here, if I calculate this heat, that's going to be same as delta U because work is 0. According to first law of thermodynamics, delta U is equal to Q. So let's calculate this one first. Q is equal to NCV delta T. Q is equal to NCV delta T. And we need to know more information because we don't have the mole and we don't know which gas it is. So let's say the mole is 1 mole and this is a monoatomic gas. So now we have all the information. N is going to be 1 mole. For a monoatomic gas, CV is going to be 3 by 2. For a diatomic, it's 5 by 2. For a triatomic, it's 7 by 2. It goes like that. So here we have monoatomic gas, so this is going to be 3 by 2, right? 3 by 2 times R. Then delta T is going to be final minus initial. Okay, we have to calculate the temperature too, right? So temperature, we can use the ideal gas law. PV is equal to nRT. T is equal to P. Oh, instead of using this one, there's an easy way. But we have to find one of the temperature to make the relationship. Let's calculate T1 and then I show you how to calculate others easily, right? PV is equal to PV over NR. So in the initial one we have 1 atm. So I am calculating T1, 1 atm, and in the initial one we have 20 liter times 20 liter, and then to convert this one into joule we have to multiply this one by 1 over 1.3 divided by N is 1 mole time 8.31, gas constant is 8.31 joule per mole Kelvin, right? So this is what we get, and if you calculate this one, that's going to give you 243.8 Kelvin. Now we have T1 at this location. T1 we found out 243.8 Kelvin. How about T2? How can we calculate this one? You can use the same formula, but instead of using this, there's an easy step for this one, right? There's an easy connection. Like if you look at the PV is equal to nRT diagram, P is directly proportional to T. Also, V is directly proportional to T. So if the P is increased by a factor of 2, T also going to be increased by a factor of 2. If the V is increased by a factor of 2, T also going to increase by a factor of 2. So if you look at this one, at P1 we have 1 atm, at P2 we have 2 atm. So the pressure is doubled right here. So to calculate the temperature, all you have to do is simply multiply this temperature 1 by 2, and that's going to give us a T2. So if you calculate this one, T2 is going to be 487.6 Kelvin, right? So this is for T2, and in later you may need T3 because when we go to this process, we need T3. So T3, to calculate T3, if you look at the volume right here, pressure is constant, pressure doesn't change, but volume is changing. So if you look at this one, volume is also directly proportional to T, and it's 3 times of this volume, right? 20, and this is 3 times of that volume. So all you have to do is multiply this value by 3, and that's going to give you, if you multiply by 3, that's going to give you 731.4 Kelvin, right? And that's how we do this kind of things. Now we can go ahead and plug these values. Delta T for, we are doing 1 to 2, right? So this is 1 to 2, 1 to 2. So 2 minus T2 minus T1. So that's going to be 487.6 minus 243.8 Kelvin, right? R is going to be 8.31, and if you plug all these values, that's going to give you 1 to 2, yeah, Q 1 to 2, that's what we are doing, right? Okay, let's see. Q1 to 2, yeah, if you plug all these values, that's going to give you 3039 joule. Since Q is 3039 joule, as we found out before, if the W is 0, delta G is going to be equal to Q. So we can say delta G also same value, 3039 joule. And if you use the equation, you're going to say apply the same thing. So you will get the same answer, right? So this is the answer for the first part. Q1 to 2, right? And then we have work. How about 2 to 3? Can we find anything? Because we know that to find anything, we have to know the information whether it is isochoric, isothermic. We know it's definitely not isochoric. Isochoric is always vertical line. But we also know this is not isobaric because isobaric should be a straight line. Do we know this is an isothermic, or do we know this is an iso? What else we have? Adiabatic. We don't know any information, right? So we cannot really do anything about this one. Let's go to the 3 to 1, right? So from that one we can find something. So here 3 to 1, we know that that is an isobaric process because that's constant pressure. If you look at the 1 atm, 3 1 atm, so constant pressure. So whenever we have isobaric process, we can use W is equal to P delta V. So that's going to give us the work. Or you can calculate the area below this one, that's going to give the work too. But let's do in this way and see what we get. So here we have pressure, that's 1 atm times delta V final minus initial. So it's going this way. So whenever we have in PV diagram, if a process go this way, it's always negative. If the process go this way, it's always positive. So here this is definitely going to be positive, and if you look at the delta V, you will know this is going to be 20 minus 60. 20 minus 60, right? It's liter. Now we have this one in atm liter, so we have to convert this one into joule. To do that, we simply multiply this by 101.3 joule per liter atm, right? And if you calculate this value, that's going to give you negative 4052 joule. How about Q? So Q here, whenever we have constant pressure, when we have constant volume, we use this one, NCV delta T. Whenever we have constant pressure, we have to use NCP delta T. So CP for a monoatomic gas, CP is going to be 5/2. For a diatomic, 7/2. For a triatomic, 9/2. So it goes like that. So here we have monoatomic, so we are going to use 5/2. So let's use this one. Q is equal to NCP delta T. So here we have one more. CP is going to be 5/2 R, and then delta T is going to be final minus initial. So we know that T1 already. T3 we know that already here. We calculated that one. All we have to do is simply subtract. So T1, where is that? T1, here we go. This is T1. 243.8 Kelvin. 243.8 minus T3 is right here, 731.4 Kelvin. Right? All of them are in Kelvin. And this R is joule per mole Kelvin. So mole and Kelvin cancels. And if you plug this one in calculator, that's going to give you negative 10,130. So this is negative 10,130 joule, right? So that's going to be our Q. To find the delta G, you can use NCV delta T, or you can just use the first law of thermodynamics. That's easier. So first law of thermodynamics is Q is equal to, delta G is equal to Q minus W delta U is equal to Q minus W. We know that Q is negative 10,130 minus, work is also negative, minus 4,052 Joule. And minus minus become plus, and that's going to give you negative 6,708, 78, 6,078 Joule, and that's going to be the delta U. And that's how we do this kind of problems. I hope you guys find this video helpful. See you next time.